Let's consider now acids and bases, a very important area of chemistry. And we're going to mainly use the Bronsted-Lowry definition of an acid and base. And in this case, an acid is a proton donor and a base is a proton acceptor. So these are the definitions of an acid and a base that we'll mainly use in this class. So let's do a couple of examples to illustrate this definition. First, what do we mean by a proton? Well, if you remember the hydrogen atom, it exists as a proton in the nucleus and an electron outside of the nucleus. So if we take the electron away and form the hydrogen plus ion, all we have is a proton from the nucleus. So a proton is an H plus atom. So a hydrogen plus ion. So it's called a proton. So an acid is something that donates a proton or an H plus ion, and a base is something that will accept an H plus ion. So let's look at the general chemical reaction of an acid. And we'll do this in water. So I'm going to represent an acid as HA. So this represents just an acid, and A can be some chemical formula. It could be an atom like chlorine. We could have hydrochloric acid, or it could be some other formula like acetic acid, and so this would contain carbon, hydrogen, and oxygen atoms. So we're just going to let this A here stand for some chemical formula. So we don't have to write complicated chemical formulas. I'll just write this abbreviation for an acid. So this hydrogen is the one that will be donated in the form of H plus, the H plus ion. So when this hydrogen is donated, it's donated in the form of H plus. So hydrogen's electron has been taken away and it stays on the A part, the rest of the molecule. And so what we'll have is A minus left over. So an acid will donate a proton to something, and what will be left over is A minus, where A stands for some chemical formula. So let's do an example of an acid. And acids are used in solution, and so we'll do an example of an acid in water. So here I'll just have a general reaction of an acid with water. So an acid is a proton donor. So this acid is going to donate a proton. So it's going to donate the H plus ion. And the base is something that's going to accept the H plus ion. So in this case, water will act as a base and accept the H plus ion. And what we'll have in return is the H3O plus ion. So we started with two hydrogens and oxygen, and we added an H plus. So we have three hydrogens. the oxygen, and we have the plus charge coming from this H plus. And what we have left over is A minus, because this hydrogen's electron stayed behind on the A part of the molecule. So this is the general reaction of an acid in water. So in this case, water acts as the base. Because it accepts the proton, H plus. So this is just the general reaction of an acid in water. Let's look at the reaction of a base in water. So I'll just represent B as base. So B stands for some molecular formula. It could be NH3, say for ammonia, or some other base. But I'm just going to represent it B just so I don't have to write a lot of atoms and their molecular formulas. So we have a B base, and we put the base in water. So now B as a base is a proton acceptor. So it can accept a proton from water. Water can act as an acid or a base. So water can donate the H plus ion to the base, and the base will end up with this H plus ion. So we'll have the base and the H plus ion bonded together. And then what's left over from water, so we've lost one hydrogen, so we have OH, and this hydrogen atom has left its electron behind on water because it left without its electron, so the OH has a negative charge. So a general base reaction in water gives BH plus and OH minus. So these are the two reactions, base and an acid in water. So you want to be able to write these chemical reactions, just a general acid-base reaction in water. Be familiar with them and be able to write them. So now let's look at the difference between strong and weak acids. So an example of a strong acid is Hcl Hydrochloric Acid, and it reacts in water. Donates a proton to water, so water ends up as H3O plus, and what's left behind after the proton leaves is chlorine with the electron from the hydrogen atom, so we have chlorine minus. This is the general reaction of the acid in water. In a strong acid, this reaction goes all the way. So in a sense, this reaction goes all the way to the right, all the way to products. So there's no HCl left over in solution practically. So we just say this reaction goes to completion or 100% product formation. Hydrofluoric acid is a weak acid, and what we mean by a weak acid is only a small part of HF reacts with water and donates a proton. So now we have an equilibrium. So we have a forward and a reverse reaction, because for a weak acid, only part of the HF reacts. So we have an equilibrium formed, and the forward and reverse reactions become the same rate as we saw before with equilibrium. So weak acid forms an equilibrium with water. And so we can define an equilibrium constant. So the equilibrium constant is equal to the concentration of H3O plus and fluorine minus divided by the concentration of HF and water. But we saw before, we don't include the concentration of water because it's a pure liquid. And so we can take the concentration of water to the left side of the equation, and we'll have that, and then we can combine K times the concentration of water, which is a constant because it's a liquid, pure liquid. Then we call this K sub A. A stands for acid. So K sub A is equal to this equilibrium expression. So now we have a weak acid forms an equilibrium, and we have an equilibrium constant. So now let's consider bases. One base is sodium hydroxide. And sodium hydroxide is a solid. We drop it in water, it dissolves or dissociates to give sodium plus OH minus. So here we formed a base directly, producing just OH from the dissociation of sodium hydroxide, similar to how sodium chloride will dissociate into water. So here we form OH directly, not through water, but just the dissociation of sodium hydroxide. Another example of a base is ammonia. Now ammonia is a weak base, so not all of the ammonia will react with water, so we'll have an equilibrium. So ammonia is a base, it's a proton acceptor, so it will accept a proton from water. And we will end up with NH4 plus. So we started with NH3, we added another hydrogen, so we have NH4, and we have a plus charge because this hydrogen left its electron behind on the water molecule. So what's left with water is OH minus. So this is the general reaction of a base with water, and this is a weak base, and so we have an equilibrium formed. So we have a forward and a reverse arrow, and we can write the equilibrium constant, and we're going to not include water, it's lopped in with K, and we'll call that product K times the concentration of water, KB, so B stands for base. And so this equilibrium constant will be the products divided by the reactant concentration, and this is the equilibrium constant for a weak base. So this B stands for base. So we have our equilibrium expression. So we can do all the equilibrium calculations that we are familiar with from the last chapter of equilibrium with acids and bases.